So in the last video, we were talking about different types of distillation. So we went through what we would call a simple pot distillation, which is something that's simple that we just need to heat up and fraction or distill off. And that's kind of this depiction. That would be a simple distillation. So nothing too complicated, nothing too fancy, just a handful of different things that are there in that solution that we need to heat up, that we need to evaporate off and condense back down in order to collect. Most of the time, this type of situation is going to be for components that have very different boiling points from each other. So those boiling points are very far away. Maybe we've got something that boils at 50 and then something else that boils at 75 and something else that boils at 100. But that's kind of the intention of what we would call a simple pot distillation or a simple distillation method. Then we said if we get really complicated and really fancy, then we can do something like fractionation. So fractionation is the idea that we could have 50 components, 100 components, and this is just a big chemical alphabet soup yet again, that we can heat up and that we can heat slowly and control it in some form or fashion. And we can separate each one of these things individually, one by one, through a different type of mechanism. But overall, the goal is the same. We're going to heat something up. We can change the pressure if we need to. And then all at the same time, what we can do at that point is to collect them one by one as we evaporate them off and condense them down. Next up, we talked about steam distillation, and we said, listen, if we need to heat something up and we need some hotter temperatures, we don't necessarily have to heat that solution up directly. We can use something else to heat up that can get a little bit hotter. And that hotter stuff, aka steam, in this type of an example, can venture off into the area that our sample is in, and that super hot steam can actually do some of the separation, evaporation, condensation steps for us in the distillation method. So this was kind of a quick review of the different versions of distillation that we talked about. And in addition to that, we said, listen, that's distillation. These are separations of samples that are very complex, that have a bunch of different components. But we also have something called stripping. And stripping is the idea that we're going to separate liquids just like distillation. But in stripping, the sample is way simpler than what we would find in a distillation method. So typically 2 liquids, and those 2 liquids have to be separated. And a lot of times, again, it does use something like steam in order to achieve that separation for us. So in this video, I told you we're going to continue on and we're going to keep talking about distillation, keep talking about some terms, and that means more words. So we need to figure out more words, more terminology. What do they mean? What does that actually stand for when we see these words that are out there in literature? And I think one of the very first ones that really gets people is this word called volatile. Volatile, okay, I know volatile people. I can tell you right now a handful of different names that I can look at and say, woo, stay away from that person. They're volatile. You don't want to get near them. Well, that doesn't quite mean the true definition of volatile as far as the laboratory area goes, as far as science goes, as far as manufacturing goes. Volatile in our type of situation basically means it can easily turn into a gas. That is all that volatile means. This volatile does not mean it goes boom. That is not what goes on here. Volatile just simply means it can evaporate very easily. That is what that term means. So for instance, if I take acetone, maybe, you're using that to take fingernail polish off or toenail polish off. I don't know. But let's say that we've got a bottle of acetone and we spill some of that acetone on a countertop. That acetone is not going to stay around for a long period of time. It's going to evaporate very quickly. Almost, it will be gone by the time I grab a paper towel and turn around and begin to wipe it up. I mean, this stuff just disappears very quickly. that means that acetone is very volatile. The same way actually with some of the alcohols. I can take some alcohols in the lab or on a countertop, and I can squirt some alcohol onto a countertop in a room temperature type of room, and it's going to maybe take a little bit longer than acetone, but sooner or later those alcohols are going to evaporate off. And because they can easily evaporate, that means that they are very volatile in nature. That is what that actually means. Volatile does not mean it goes boom. Volatile does not mean it can blow up. That is not the proper definition of the way that we treat this particular type of term in a scientific type of setting. So anything that evaporates quickly will be termed volatile. It does not mean it can be used to make a bomb. That is not what that word means at all, period. Okay, so just a little bit of terminology cleanup here, because what we're getting ready to kind of talk about is that the components that go into something like distillation, it's going to be great if they are volatile. And the reason is because they evaporate easily, which means they don't need a lot of heat in order to evaporate. They don't need a lot of energy input in order to get them to turn into a vapor and travel up a column and through the other side through a condenser, aka, in order to be collected. So whenever we get volatile substances, that is great news for us. We can do a lot of the cleanup, we can do a lot of the purification quite easily with those types of compounds. Again, without an issue, without any problems most of the time. As far as volatile goes, many times our organic solvents that we use in the manufacturing realm or in a laboratory setting, those are going to be notoriously known as being very volatile. So a lot of the organics, a lot of the typical solvents, a lot of the basics of those types of situations, we try to find the cheapest that we can, but at the same time, we also try to find things that are very volatile that can easily evaporate. So that way, if we've got to do some of these cleanup steps, if we've got to do some of these purification steps, we're not wasting a lot of time and energy, literally, in order to separate these off and collect them, to recycle them, or to get rid of them as waste. So volatile is going to be the key here for sure. Distillation. Why do we do distillation in a particular type of production facility? Well, distillation can do two major things. Of course, many other things can happen, but two major things. First is just the production of distilled water. That is what distilled water means. So distillation, distilled water, it is the concept that, hey, I can take something that looks like this, and I can put water into the flask over here. And that water, like I said before, out of the tap is a chemical soup of different things. There's organic pieces there. There's inorganic pieces there. There could be bacteria that's going to be there. Hopefully that stuff is dead. But there's a ton of different stuff that's in tap water. And we need to clean that up. That is not suitable to be used. So we can heat that up. And as we heat it up, it will evaporate and it will turn into a vapor. And it goes up and it goes through a condenser and it begins to condense, aka gas turns to liquid, and we can collect that clean water on the other side. That is distilled water. That is the process of distilled water, and actually it's one of the cleanest in the grocery store that you can purchase in the water bottle aisle. Now, reverse osmosis, that also does a very good job filtering. It does a very good job for purification, but before reverse osmosis came around, distilled water was actually a very good quality, very clean type of water, and very cheap at the same time than something else like a Deer Park jug, something that doesn't have any type of purification at all. It's just literally out of a tap. So production of distilled water, very commonly done through the process of distillation, and it is a chemical complex soup because, again, we're looking at things like calcium and magnesium and some of the volatile organic compounds that might be present. Trihalomethanes could be present, chlorinated compounds, brominated compounds. Again, an alphabet soup of different things that's in tap water by the time it reaches to you. For the most part, though, it should be deemed as safe in order to drink, but still it's an alphabet soup. There's things that are there. There's things that need to be purified. It is not the cleanest that it can get. So distillation will help take care of much of that. Next up is separation of alcohol from water. And this is typically done in distilleries, of course. So, if I go to Front Street Brewery, or if I go somewhere that's kind of making their own beer, making their own wine, fermenting their own alcohol in some form or fashion, there is a process that they can undergo, and that process is distillation. And this allows us to drive the alcohol away from the water content. So we can increase the alcohol concentration and increase the proof, and really kind of play around with the percentages of alcohol that are present in those particular types of samples that we obtain on the very, very end of the process. All right. So just a couple of examples of distillation, and I think that kind of sums that up. Hopefully you get a really good feeling of what distillation is now, and if you do, that's great, because we're moving on. And now what we're moving on to is some more terms, more words, and these are going to be precipitation and precipitate. So precipitation is not this. This is not what we're referring to. Now, I know we call this precipitation, right? Rain, snow, sleet, hail. I mean, I've actually said this before in another video and some other slides. And we're like, hey, water evaporates and then it condensates. And then when it condenses down, it gives us all of these different types of water in different forms, depending on how cold the weather is, blah, 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 blah. All right, this is not precipitation. It is precipitation based on weather, but not quite in a laboratory setting or in a production setting. But I think it does a very good job getting the idea across, because what's happening is that we've got water vapor, and that water vapor is up there above our heads, and then sooner or later something's going to happen, and that water vapor is going to crash out. That water vapor is going to come back down to earth, onto the ground, and onto our heads if we're unlucky. But precipitation, that is kind of the reason that they use that term. But precipitation in a scientific type of setting is something similar. It's just a little different. So precipitation is the process of taking a gas or a liquid and precipitating out a solid, making a solid fall out of solution, so that way we can visually see it and maybe capture it and maybe do a little bit of cleanup on it in a later step. Or there is a chance that the precipitate is the trash. Maybe, just maybe, that precipitate is hazardous waste. And if we can precipitate that out of there, we can do a waste disposal of that. So, for instance, I'll give you an example. Let's say that I've got a beaker, and this beaker's got a solution in it. I don't really know what that solution is, but the company has deemed it hazardous. And the reason that they've deemed it hazardous is because there's silver that's on the inside, and silver cannot be dumped down the drain. Silver cannot go down the waste disposal. Silver has to be treated of as a hazardous waste, which means that we're going to have to pay someone in order to come in to take that waste from us and dispose of that the proper way. But they're going to charge us based on volume. And if I give them liquid and I'm like, here's 50 gallons of the stuff, then they're going to charge me for 50 gallons of silver waste. So there is actually a piece here that we can be creative with, and we can be like, hey, there is a chance that maybe, just maybe, that silver that's causing the problem that's in that solution, maybe, just maybe, I can precipitate that out. So what can happen here is that I can add something that is chlorinated. So something that carries a little bit of chlorine with it. It can be something very, very simple, as long as chlorine is actually there. So when chlorine hits that solution, chloride, not chlorine, but when chloride hits that solution, what we'll end up with is a compound called AgCl, which is silver chloride, and this is a solid. So what happens after I add the chloride is that we've got this silver solution, right? It's a solution that contains silver, and the chloride is going to precipitate that out. So precipitate, I like to use the abbreviation as PPT for precipitate. And what we'll end up with is a solid that begins to form, and that solid begins to fall out of solution. and that solid begins to settle on the bottom of those containers. And that is where the silver is at now. So what I can do at this point is, if I make sure that all the silver is out of the liquid, then I can take that liquid and I can dump it, I can process it in a completely different way, because silver no longer is involved. Silver is now precipitated out, all the silver is now gone, and that silver is all into a nice little bitty smaller solid chunk at the bottom of this container. So I don't have to get rid of 50 gallons of silver waste now. I can just get rid of a little smidgen of silver solid waste, and maybe that's going to be a little bit easier on the pocketbook. So precipitation is going to play a role in the bioprocessing manufacturing line, but also in the waste disposal as well, because again, if we can be creative, we can use precipitation to gather things and separate things, so that way we can limit the waste that we're generating, we can make smaller volumes or quantities of stuff that have to be processed. Or at the same time, maybe it's that we need to gather. Maybe that's what we need to keep. Maybe that's what needs to be separated off and kept, so that way we can do further purification down the manufacturing line. And if so, that's okay. But again, I think the importance here is to understand that these processes will help both routes. It will help the production route of making something that we're supposed to be making, but these processes can also help us manage and limit the waste that's coming on the other end. So a precipitate is the name of the solid that is given once it falls out of solution, and precipitation is the actual process of it falling out of solution. So just a little two terms, again, terminology, use your words. I mean, that's what this is all about. And I think that as long as you remember precipitation in this point, then you get an idea of what's kind of happening as far as on a mass production type of scale, or even in a laboratory type of setting where things are precipitating out of containers, out of beakers, out of test tubes, whatever the case might be. Precipitation is there. So precipitation can be achieved a number of different ways. You know, how do we do this? Well, in that example, I said we add chloride. Well, adding chloride does not necessarily fix it every single time. It really depends on what we need to gather, what we need to capture, what we need to isolate. And there's a couple of ways that we can do this. And the first one is a chemical reaction can lead to a change that will make it a solid. So that is what number one is. It says chemical reactions change the solute to an insoluble form. That is what that means. So I've added something for a reaction to take place, and that is a chemical change. And that chemical change is producing a solid that is falling out of solution. No longer is it soluble in the solvent anymore. It is falling out. I visually see it. It is there, and I can pick up on it. I can take pictures of it. I can describe it, but it is not by no means anything really, really tiny or anything really small. These are very evident changes that begin to take place most of the time on the production side of the house, if we are working with very large quantities, of course. Number two, changing the pH can change the charge of the solute molecule, causing them to come out of solution. Absolutely. So what this basically means is that maybe I don't want to add anything new. Maybe I don't want to add another chemical on the surface of the solution or inside of the vat, whatever the case might be. But if I can play around with charges and if I can play around with pHs, then that can make things fall out of solution just as easy. So if I have a solution and it says take it to acidic or take it to alkaline conditions, aka basic, then I just play around with the pH of the stuff, right? I make it lower, I increase it, I make it higher, whatever the case might be. That could be enough in order to get something to fall out of solution. And as long as things are falling out of solution, that is a good day in the world of precipitation. So that's another way that we can encourage precipitation to take place. Number three, it says adding a solvent that does not dissolve the solute and it causes the solute to come out of solution. So what does that mean, Tracy? All right, well, I'll give you another example. Let's say I've got a container, and this container's got some liquid in it, and this liquid has my solute, and that solute is, of course, completely dissolved. Okay, well, that's great, but I need to precipitate that out of there. So if I don't want to add a chemical reagent, if I don't want to add maybe something like a solid to that in order to force that out, or maybe pH changes are not going to cut it for me, that's also not going to make it fall out of solution. There is another option that we have that we can use both on manufacturing and in a laboratory setting, where I can use another type of solution. And that solution is going to be something that the solute, which is the stuff that is dissolved, is not soluble in. And soluble means, of course, it breaks apart. So what I can do is that I can take this solution or this liquid, and I can pour it into that container. And when that happens, if I add enough of it, it actually disturbs the stuff that is dissolved so much. And it's like, oh no, I hate this solution. I don't like this liquid. I cannot dissolve in it. What am I going to do? It's forcing me out. And that's exactly what goes on. So it forces the solid out of the little tiny smidgen of solution that it is dissolved in. And we start to see a precipitation reaction here. So I call this soluble, and it is by definition soluble, of course. A solid dissolves in a liquid that is soluble or insoluble. That's what those are. But it is the liquid properties that are making it do that. So I can add a solid in and make it fall out. I can change the pH to make it fall out, or I can add a liquid in to make it fall out. Any of those are perfectly okay. Here's an image of a precipitation reaction taking place right in front of your eyes, almost in a way. So this is a reagent, and that reagent is a liquid. So we are adding a liquid into a container, and that has some stuff in it. And this stuff is actually lead, which is like silver. We cannot dispose of that down the drain. So there's a chance that I might want to recover the lead. I want to encourage it to precipitate out. I want to keep it. I want to capture it. So that way we can minimize our waste and get rid of a large portion of that volume, that liquid that might be in the beaker. So if I can remove the lead, then maybe I can do that. So this is a solution that will make lead fall out. And when it does, it creates this yellowish type of precipitate. I see it with my eyeballs in the picture. And if I allow that to settle, it will settle to the bottom. Or I can put it in something called a centrifuge, and that centrifuge will be able to pull that solid down to the bottom of that container much faster and much quicker, and I don't really have to wait on it. So another term that's getting ready to pop up or bubble up here in a way is this term called crystallization. And crystallization is not the same as a precipitate. So that's where I'm going to stop this video. In the next video, we're going to pick up with crystallization. We're going to talk about maybe how this is a little bit different than precipitation, and when is it right to use one term and not the other. So in the next video, that's where we'll pick up. Come back and see me. I'm not going to go anywhere. So go ahead and hit play on the next one. You've got nothing else to do. Go ahead and knock out another one. You're on a roll. You're doing such a great job. Take some more notes. You'll be great. I promise.